His schedule more than
Progress.
Fine. Can you hear me?
Yes, sir.
Okay. Okay. So the last lecture I was talking about some ways to apply group theory in counting combinatorics problems. So we were looking at a topic called group actions. So that was one application of groups which we were able to see. But as I explained, that there is a much more complex hierarchy involved in this topic called abstract algebra, and groups are only the starting point of it. And you can study more complex examples of abstract spaces such as rings and fields also. And in particular, we are done with geometry and combinatorics now, so we are going to move on to algebra. So that is where we'll be studying topics like polynomials, inequalities, where these ideas of rings and fields will come up much more often. So with that in mind, I was thinking of starting today with some discussion about polynomials, or in particular one aspect of polynomials, which is particularly for us, when we talk about real valued polynomials or complex valued polynomials, so that is complex numbers. So I guess many of you, or even most of you, might have already been introduced to the basic notion of what is a complex number. So what I want to do here is, I'll just quickly go over that, but more importantly, I want to focus how complex numbers relate to other topics which we already studied. One of them being geometry. So representing a point on a plane with 2D coordinates, which we already do in real numbers, that is one thing. But we can also do the same with complex coordinates, and there are some useful properties related to geometric transformations and that. Uh, yes, this was supposed to be the exam meeting. When you say exam meeting, do you mean the discussion of the pre-RMO paper?
Excuse me, sir.
Yeah, I didn't get
Uh,
your question.
Sir, actually, we have an entrance test right now, and it has already started on the server.
Okay.
So
Uh,
we were supposed to join this meeting for keeping our camera on.
oh, sorry. Then this is not that meeting. I'm taking, this is the normal Olympiad lecture. Okay, if you are taking an exam, then I think you should disconnect and join that.
But this is the meeting link that was given to us.
Uh, is that the case? Because this meeting I have posted on my personal ID, so uh, I think there is some confusion.
Yes.
So can anybody raise your hand if you are also for the same reason? Okay, I think lots of students have joined for that reason, it seems. No, I think there is some confusion. So then you better disconnect, and I'll message Subodh sir. Okay. So those who are staying, I'm assuming that you are here for the Olympiad lecture. Otherwise, I'll suggest you to disconnect. Okay. So just give me 1 minute. I'll clarify this with Subodh sir. Okay, I'll put the link to the entrance test on the group, so you can join that. Okay, but yeah, I mean, don't stay in this lecture if you're writing any exam. Okay, so anyway, I'll continue the topic. Is the case that everybody has joined for the exam, or is anybody who has joined for the Olympiad lecture? I don't know what's the confusion.
I'm
So
joined
we
for
are joined for
Olympiad
exam.
lecture.
Okay, fine.
No, I
So,
also have
those
to.
who
Yes,
are
sir.
here for
I
the
also.
lecture, you can stay. Okay. Yeah. So I'm just forwarding the right link on our Olympiad group. Okay. Others for the exam, you can join that one.
So which link should we join for exam?
The one which I posted just 1 minute ago on the our WhatsApp group.
Recording in progress.
Okay. Are you able to see that? Okay. Anyways, I think students can figure it out. Okay. So yeah, coming back to what we want to do today.
Sir, I have a doubt in one previous question you have done.
Okay, sure. Tell me.
Sir, in that problem of placing n square kings into n cross 2n board.
Okay.
So, sir, we assumed that the up, down, and left, right are separate. We can
Yes. Yes.
separate them.
Yeah.
But,
Correct.
sir, when we place a king in the right bottom corner of a 2 cross 2 board and on the left up corner of another diagonally opposite 2 cross 2 board,
Okay.
then, sir, I think that is not allowed.
What? 1 minute. Right. Okay, so let us say you can see my screen, right?
Yes, sir. So, with yeah.
Okay, so suppose the middle 2 cross 2 block, I place a king at the right bottom corner, right?
Yes, sir. Sir, can you draw? Oh, yeah, yes. And on the r- down rightmost corner,
Mm-hmm.
you place a king on the that.
Okay.
So, sir, in our n plus 1 raised to 2n plus 1, we have counted this, but I think we should not count this, right?
Hmm. Yes, yeah, you are correct. So I think we need some different strategy to count in that case. Uh, Let us see how can we modify our approach then. Okay, is everybody able to remember this problem and understand the issue with our previous solution? So the question was in a, let's say here I've taken 2n, so n is 3. So 2n cross 2n, so 6 cross 6 board, how many non-attacking kings can we place? So the answer to that we found by pigeonhole principle that it will be n square, so 9. So we want to place 9 kings on this board. And obviously by the same pigeonhole principle, each of these 2 cross 2 boards will have exactly one such king. So the idea which I had suggested was that for every such 2x2 block, we have to take a decision whether the king is to the left or right and up or down. And I felt that we could take this decision independently, but as it turns out, there are cases where that is not true. So we need to think what we can do for that. So I think this problem does not occur when, because we had started with the simplest case where, let's say, we had only single row. So if you have single row of 2x n blocks, then I think this strategy works just fine, right? Because here only the left right matters, the up down does not matter. So I think the answer that we found in this simple case of 2x2n, that is correct. But the moment we generalize this to, I mean, even if we take one step from here, we go from 2x2n to 4x2n. I think that is where things can start to go wrong. Is that correct?
Yes, sir.
So this is where. So I mean, again, as usual, we should try and find the solution to the simplest version of the problem. So 4x2n, or even for that matter, 4x4. So even if you have a 4x4 board, I mean, this is a case where we can actually count by hand the number of possibilities, and we can sort of cross check if our formula is giving the same answer. So in a case of 4x4 board, uh, previously what we had said was that on every row, so for example, the first row, the kings can be placed in three possible ways, like left, 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 right, and right, right. And same for the second row. So total number of ways to choose the left and right combination is 3 for the first row and 3 for the second row. So total 9 ways. And similarly, up down can also be chosen in 9 ways. So therefore, our answer was 81. But in that, based on the new understanding, we will be mistakenly counting cases like, for example, if in one case the king is here and here. So uh, So I think this is one case that will get accidentally counted, and this will be the other case that will get accidentally counted. But I don't think there is any other case which will get counted by accident. So I think the answer should be 81 minus 2, which is 79. Okay, is everybody following this?
Yes, sir.
Okay. So at least in this case, we were able to figure out exactly how much wrong counting we are doing and subtract it out. Now I'm wondering whether we can generalize this strategy to 4x2n board. That, I mean, by the same method which we applied in earlier, which was incorrect, but we got the total number, and out of that, if we just subtract the number of times we will do this wrong counting. So, for example, at every such intersection, there is the possibility of such wrong counting happening. But I mean, as I imagine, the possibilities will quickly grow out of bounds, and particularly this 2n being variable, right? I mean, there will be a lot of cases involved. For example, there could be two adjacent blocks where this happens, or there could be some distance between them, etc. So in general, this could be fairly complex. Also, I mean, this number 79 is a bit, I mean, there is no clear pattern. This, it seems to be coming from nowhere. So I don't know. Okay, I think let's give this some thought to this problem. And if you also have any other ideas, in particular, one possibility I'm thinking somehow if we can apply inclusion exclusion type strategy, because that works many times, because it's a, I don't know. I mean, the reason why I'm thinking of inclusion exclusion is because uh, here we have a condition like no two kings should attack each other. So we can always flip that, and let's say, I mean, if I start to call this set some say these blocks some names like A, B, C, D, E, F, G, H. Okay, then in my universal set of all combination without restrictions, So in other words, all the ways to place the kings. I mean, I don't change the number of kings, but without any condition on them attacking each other or not, then I can start to make sets like let A1 be the all sets where A and B do attack each other. So I'm forcing that A and B attack each other, and in a way, I mean, counting that turns out to be easier. And I mean, the problem is I have to consider this set for every pair of adjacent cells. So I have to consider a set for A and B, A and F, A and E, etc. So I mean, as such, this number of such sets will increase very quickly. And I mean, not only counting the sets should be easier, but counting the intersections of the set. So intersection of A1 and A2 should also be easy to count. But if we can figure out a way to do that, then I think inclusion exclusion could give a possible way to solve this problem. Okay, but anyway, I'm just suggesting some ideas. I will also have to give it some thought. But yeah, I think I'll encourage you to also try some experiments and see if we can find some solution. But yeah, definitely, I think there is a problem with my previous approach. That is okay. Okay, so getting back to what I want to discuss today, as I said, we want to eventually talk about polynomials, but one way to approach that is through complex numbers. So, in a way, I want to demonstrate some ideas from complex numbers which are useful in geometry also. And I mean, how we can use complex numbers to solve some geometry problems. In a way, I mean, those you can also do with coordinate geometry, but complex numbers have a bit more power because, in a way, yeah, like two real numbers can be folded into one complex number, the real part and the imaginary part. But more than that, I mean, the overall space of complex numbers has much more rich and interesting properties than just the coordinate system. So that gives us lots of flexibility. Okay. So that is the motivation for today's lecture. And in a way, I want to tie this topic also to what we did last time, which is the whole field of abstract algebra, like groups, rings, and fields. Because I want to demonstrate to you how complex numbers were constructed. It is not like, of course, we all know that the I, which is, we call it the square root of -1. And that allows us to have solutions to equations which otherwise will not have a root. Like, for example, x square plus 1 equal to 0. This equation does not have a root in real numbers. That is why we have to introduce this variable I. But there is a broader philosophy to this which is interesting, and that could be useful elsewhere also. Okay, so for example, if we take a case of, I mean, start with simple integers. Okay? So there are some polynomials in integers, like coefficients being integers, which do have roots. Like, for example, 5x equal to 0. This has a root, x equal to 0 in integers. But some equation like 5x equal to 1 does not have a root. X cannot belong to integers. So when something like this happens, same as what we did here. So we introduced a new variable I, and in a way, I mean, instead of writing I as this more formal or sort of more consistent way of introducing I is that I is nothing but the root of this equation, which does not belong to the set we already have, which was real numbers in that case. In the same way, here I can introduce a variable, and let's just call it t. Okay, so I've created a new variable t, or new constant, you can say, which is, it's an axiom that I assume that t is a solution of this equation. Okay, so it is given that 5t equal to 1. Okay, but clearly t is not a part of integers. But given this symbol, what I can do is extend integers by one level. So I can extend set into a larger set. Okay, so which I will temporarily call, there is no standard symbol for, let me just call it S for now. Okay, so this new set S, I mean, to begin with, it only contains all the integers and now this new variable t which we are introduced. Okay, and now what I can try to do is, on this new set S, I want to try and define all the operations on integers that we already know, which is addition and multiplication. So any two elements of S, if I can figure out how to add and multiply, then I have a complete sort of valid algebra for S. So for example, I could talk about 1 plus t. So I mean, how to add two integers within S, we already know that is the same rule as the normal set Z. But in particular, how to add this new element t with any of the existing ones. So for example, this 1 plus t, I need to figure out some way to define that. So if I don't have any way of expressing this formally, I just have to keep this symbol as it is. So 1 plus t is also one new member I have to add in this S. Same will go for 1 plus t, 2 plus t, etc. So in fact, t plus any element of integers, this will be a new element of my set S. Not only that, I can multiply t with any real integer also. So if I multiply, take any integer p and multiply p with t, I will again get a new member of S. So in general, you'll see that S will contain all expressions of the form pt plus q, where p and q are integers. Okay, are you able to follow this?
Yes, sir.
Okay. And now, I mean, so far I've never used the word rational numbers, but if we talk about rational numbers, you'll see instantly that, I mean, writing t every time is silly because we know that t is nothing but 1 plus 5. Okay, but I want to indicate to you how that the fact that t is 1 plus 5 is not important to do this algebra in this way. However, there is one small point, and in a way, I think you can see a lot of similarity between this and how we define complex numbers, right? I mean, if I just draw, define complex numbers to the right of this, I can define C as nothing but the set of all AI plus B, where A and B are real numbers. So here, almost line by line, you can see the similarity. And here, I mean, in this case, T is the root of the equation 5x equal to 1, and here I is the root of x square plus 1 equal to 0. Also, you will be careful to note that I am saying I is a root of x square plus 1 equal to 0 because, I mean, x square plus 1 equal to 0 in the complex domain we know has two roots, the I and minus I. But as it turns out, the choice about which of them you want to call I and which of them you want to call minus I is completely arbitrary. Okay, so if you exchange the roles of I and minus I throughout complex numbers, nothing changes. So the entire geometry remains constant. I mean, algebra remains constant. So in a way, it is like in physics, you may be aware that, I mean, we say by convention that proton has positive charge and electron has negative charge, but those plus and minus signs are completely arbitrary. So if you flip them, the physics doesn't change. In that way, I is just one of the possible roots of x square plus 1 equal to 0. Okay, so this is how we can construct this set S. However, so there is a small difference between these two constructions, and that is uniqueness of representation. Okay, which means that, so what we are saying here is that any expression of this form pt plus q belongs to the set S. But conversely, every element of set S can be also expressed in the form pt plus q. So if S belongs to, I mean, small s belongs to capital S, then S is equal to pt plus q for some p and q. But is p and q unique? So if you think about it, you'll realize that there could be multiple values of p and q which are used to represent the same element. Okay, for example, I mean, if you take some numerical case, like let's say S is equal to the number 2. Okay, then 2 can be written as 0t plus 2. It can be also represented as t times t plus 0. You see that these are both perfectly valid ways of writing the number 2. I mean, at the back of our mind, we know that t is equal to 1 by 5. So from that also you can figure this out. Or more directly also, if we, because we know that t is a root of the equation 5x equal to 1. So therefore 10x equal to 2. Okay. So it means that the P and Q exist but not unique. Okay. By comparison, in the complex domain, this is unique. So if there is some complex number z, then z can be written as a plus ib for unique a comma b in reals. So I mean, as it turns out, there are some cases where this construction is unique, has a unique representation, and in some cases it does not. And by the way, there is an example in between the two, which is important in its own right. So I just want to introduce that also. So as you see, the construction is very similar. We start with some equation and we start with some domain. So in the left side, we started with the equation 5x equal to 1. And in the right side, we started with the equation x square plus 1 equal to 0. Let me consider the equation x square equal to 2 and let x belong to rational numbers. Okay. So again, we all know that x square equal to 2 has no root in rational numbers because square root of 2 is not rational. But again, instead of doing it that way, I want to introduce a new variable to denote that square root of 2. So let use the variable t again. Doesn't no harm in that. So let t be a root of x square equal to 2. Okay. So therefore, in other words, what I am known is t square equal to 2. Okay. And again, I can construct a new set S, which is nothing but all symbols of the type a plus b times t. Okay. Where a and b are rational numbers. Okay. So I'll leave this as a homework for you to first figure out, like define addition and multiplication on S. Second, show that each element of S has a unique representation. And the third property, which we have not done enough background to prove, but if you are interested, you can figure out and read that through that S is a field. Okay. So S has a lot of complexity to it. It's a field actually, just like rational numbers are a field. And this kind of construction is useful to do a very interesting property in geometry, surprisingly. I mean, there is no mention of geometry here, but there is a very deep connection with this kind of fields, with the ability to construct numbers geometrically. So in other words, if I give you a segment, line segment of some length x, then we know how to do a number of operations on that value x. So we can know how to double the length, take the square or even square root of x. So we know how to find root of x, but we don't know how to find cube root of x, for example. So which numbers can be constructed or cannot be constructed geometrically? When I say geometrically, we mean by ruler and compass. So that whole space of ideas, in particular, which regular polygons can be constructed geometrically. So we know that we can construct a triangle or a sorry, I got disconnected from it. Yeah, so we know how to construct a equilateral triangle or a regular pentagon, but there is no way to construct a regular seven-gon with ruler and compass, for example. So what is the class of numbers, natural numbers, n, such that a regular n-gon can be constructed with ruler and compass? So the answer to that comes somewhere along the lines of like continuing this line of questioning. I mean, for a lot of time, it is not like just 3 steps, but there is a whole theory that can be evolved through this approach. Okay. But anyway, all of that is quite tangential to our topic, and even I'm not an expert in that, so I will also have to study that properly. But I'm just indicating the ways in which all of these topics connect to each other. Okay, but suffice to say, what I want to indicate is that this construction of complex numbers, if you go back to how we constructed the set of complex numbers, so this construction is not unique. This approach can be used in multiple different ways. And for us, for complex numbers, what matters is, so I assume everybody already knows how to add and multiply complex numbers. Can you raise your hand? Okay, okay. Yeah, I don't know if this already has been covered in our regular lectures, or this is a new topic for you.
So that will be done in 10th. We are in 9th.
I see. Okay, fine. So in that case, I'll just give you a quick introduction so that we have enough information to cover the basics. So if I have, let's say, two complex numbers Z1 and Z2. Okay. So Z1 is A1 plus IB1 and Z2 equal to A2 plus IB2, where AI, BI, these are real numbers. And I mean, the fact that there exists only one unique ordered pair AI, BI is very important. Okay. Because that allows us to do this kind of representation. Okay, so then I can define Z1 plus Z2 as simply A1 plus A2 plus I times B1 plus B2 and multiply Z1 into Z2. So I can just multiply them the way we would normally do and expand the brackets. And always keeping in mind that I is I square equal to -1. So I is the root of the equation x square plus 1 equal to 0. Okay, so these are, I mean, fairly typical formulae that you can get anywhere. Okay, so this is how you multiply and add two complex numbers. So in particular, our interest is in how we can use this in geometry. Okay, so for that, the first thing which would like to understand is that just as every complex number can be represented as a pair of real numbers. I mean, basically this A1 plus IB1 is one way of writing this complex number, but I could easily write it as simply a ordered pair like this, that A1 comma B1 like this. So in that case, it will be an ordered pair in R square. And now you start to see how this is almost looking like a 2D coordinate some point in a 2D coordinate plane. So if I draw my standard XY axis, okay, then I could plot this point at the location A1 comma B1. Okay, so as it turns out, there is a bijection between all of these sets. So the set of complex numbers, the set of ordered pairs of real numbers, and the 2D plane. So all of these three sets have a bijection. So any object you give me in one of these three sets, I can convert into the other one. Okay, is this understood by everybody?
Yes, sir.
So that is what gives us the sort of foot in the door that, okay, now there is a possibility that we could try to apply these complex numbers in geometry, but it is still not clear how, that why should this matter. So for that, I think we need to look at these basic operations of addition and multiplication. What do they mean in terms of this coordinate plane? So if we understand that, then maybe we can get some more insight. So for example, here I had one number P, A1 comma P1. Suppose I have another number Q somewhere over here, which is A2 comma B2. Okay. And so I'll start by introducing some conventions now. So in this kind of geometry, what we typically do is we use the lowercase letter. So small p denotes the complex value corresponding to the capital P, which is the point on the plane. Okay. So capital P is the actual point in the plane. small p is the complex number. So similarly, small q is the complex number which represents the capital Q point. Okay. So in other words, this point Q has real coordinates a2 comma p2, but we also say Q has complex coordinate small q. And note importantly, I am saying Q has complex coordinate, not coordinate, because it doesn't require two coordinates in the complex domain. A single number Q belonging to complex number is sufficient to represent the point. Okay. So if this point P and Q have the complex coordinates small p and small q, and then we talk about adding these two numbers. So if I take the number small p plus small q and try to plot it on this 2D plane, where will it go?
Sir, it is addition of vectors.
It's additional factor, right? It will complete the parallelogram. So it will look something like this, for example. So this will be my number r, and this is clear from the way we added, right? Basically, the x coordinate or the real part is getting added, and the imaginary part is getting added. So basically, your displacement on the x direction and y direction will simply add up. So that will give you the point r. Okay. So this was good. What about multiplication? By the way, I mean, just this addition alone is sufficient to do lots of interesting manipulation. But with multiplication, the power becomes very even greater.
Sir, product, in case of product, it is product of modulus and sum of arguments.
Product of modulus and sum of arguments. Correct. Does everybody understand this terminology, or if you want, I should explain it?
So can you please explain it?
Okay. So as it turns out, in any space like the 2D plane, but in general also, the problem which coordinate geometry solves sorry, again, my laptop keeps logging out. I don't know why. Okay. So in general, when we are talking about any space like the 2D plane or even the 3D world that we have around us, the problem that coordinate geometry solves is that it assigns a pair of numbers or a triplet of numbers to every point. Okay. And for that, we use what are called the Cartesian coordinates. Okay. So this was the system developed by Descartes, the mathematician, where he took these x and y as the fundamental axis. And so any point P, the coordinate is defined in terms of the distance from these two axes. Okay, so this is what we call the x coordinate and y coordinate. But there is more than one way to assign a pair of numbers to a point. So just as we have Cartesian coordinates, we could also come up with a different system which is called polar coordinates. Okay. And in the polar coordinates, what we do is so in polar coordinates, we divide the plane in terms of these two sets of curves. So in general, what we can do, right? There is no special reason to choose this or that system. I could create my own system where all I need is I create the family of lines in the plane or family of curves. Okay. and every point in the plane gets a coordinate based on which two lines intersect. Okay. So I could define these blue and red lines anyhow I want. And all that matters is that every point in the plane lies on exactly one line of the red family and one line of the blue family. So in the case of Cartesian coordinates, these red and blue axes were being served as the horizontal and vertical parallel lines. So for example, we had lines like this and like this. So basically every point on the blue line has the same y coordinate. So we are doing the same thing in the polar space now, but except the two families we are considering are the two families we are considering are these radial lines, red ones, and these circular lines, the black ones. Okay. So every point lies on one red line and one black line. And so that gives us a different way of assigning coordinates to every point in the plane. And traditionally, it is a good idea if these two families of line are orthogonal. Okay. Like there are reasons for that based in like physics and calculus. So for polar coordinates, do you see wherever these two families are meeting, if you draw the tangents, right, you will see that they are 90 degrees to each other. So in other words, basically the polar coordinate is defined by which black line the point lies in and which red line the point lies in. So the black lines represent what is the distance from the center, origin O, and the red line represents what is the angle that the point is forming. And as convention, we take the positive x-axis as the 0-degree line. Okay, so basically every point in the plane has a distance from the center and an angle theta. Okay. So therefore, every point in the plane now has two sets of coordinates. Okay, a traditional x and y coordinates, which are the Cartesian coordinates, and r and theta, which are polar coordinates. Okay. So here r and theta are called the modulus and argument of the point respectively. Okay. So if you know the values of the coordinates in Cartesian, how to convert them into polar and vice versa. So this is a like very simple trigonometry problem for you. Okay. So you can figure it out. So for example, I mean in this diagram itself, you have all the information required, right? X, Y, R, theta. The only caveat is that you need extended definitions of trigonometric and functions. So sine and cos, etc. I mean, you may know how to define them in a right angle triangle, but you need the definition for any real number theta. Okay. But anyway, so I mean, at a very basic, what we can do is we can convert back and forth between x and r theta. For example, x is r cos theta, y equal to r sin theta, something like this. So the definition that we have done for multiplying two complex numbers, right, z1 into z2. So that was the definition that we wrote in the Cartesian coordinates. So if z1 is represented as a1 plus ib1 and z2 is represented as a2 plus ib2, then we wrote the product whatever happens. But now if we interpret these 2 points in the 2D plane and we consider the Cartesian coordinates, so maybe a1 comma b1, this point can be represented as r1 comma theta 1, and a2 comma b2 can be represented as r2 comma theta 2. Okay, in that case the product z1 into z2, its complex value, I mean its polar coordinate turns out to be r1 into r2 comma theta 1 plus theta 2. Can you raise your hand if you already knew this property? Okay, I think only Amalesh was aware of this. Others, so then I think it's a good idea for us to go over the proof of this, because I mean it's instructive to see how. I mean, clearly what you can see is that the expression which we wrote earlier for the product, compared to that, this looks a lot simpler. So to understand that, I think it's a good idea to look at the proof once. Okay, so what I have to do is these two expressions, x equal to r cos theta and y equal to r sin theta, I can use them in this case to represent a1 b1 and a2 b2 in terms of these r and theta, right? So z1, which is a1 plus I b1. So here I know that a1 is nothing but r1 cos theta 1, b1 is r1 sin theta 1, a2 is r2 cos theta 2, and b2 is r2 sin theta 2. Okay, so if I substitute all of these values in the product that we had written earlier, so the product in Cartesian domain that we had written a1 a2 minus b1 b2 plus I times a1 b2 plus a2 b1. Okay, if I just substitute these values in this expression, what do we get? So first thing you'll notice is that in every term there is a combination of one of these terms, ai bi, and one of I mean a1 b1 or a2 b2. So therefore everywhere there will be one copy of r1 into r2 which will come out common, right? So this
Yes.
whole thing will be equal to r1 r2 into, and in the inside the bracket you will have a number of trigonometric values. So for example, if the first term a1 a2 minus b1 b2 will be nothing but cos theta 1 sin theta 1 minus cos theta 2 sin theta 2. And those who know angle addition formulae for trigonometry, they will immediately see what these
So
are all.
cos theta 1.
Yeah, so this is cos theta 1 plus theta 2,
Yes.
right? Okay, so the first bracket is sorry, this would be cos minus sin. So cos theta 1 cos theta 2 minus sin theta 1 sin theta 2. So cos minus sin. And the second bracket is sin cos plus cos sin. Okay, sin theta 1 cos theta 2 plus cos theta 1 sin theta 2. So this turns out to be nothing but r1 r2 times cos of theta 1 plus theta 2.
Sine
Plus
of theta 1 plus theta 2.
Sorry, what are you saying?
So nothing. The sine of theta 1 plus theta 2, that
Yeah,
one.
correct. Okay. Okay, so now do you see that this is correctly confirming with the expression in polar domain for the point whose modulus is R1, R2 and angle is theta 1 plus theta 2. Okay. So as it turns out, what this means is that addition is simple in the Cartesian domain, not Cartesian domain, but multiplication is simpler in the polar domain, because in the Cartesian domain, the components were adding very easily. And in the multiplication case, the polar coordinates, they are adding very easily. Yeah, sorry. Okay, so I want to give you another interpretation of multiplication, which makes it really powerful. I mean, this polar coordinate interpretation is good, but what we can do is one level above that. Okay, I want to show how polar coordinate multiplication turns out to be a geometric transformation in the complex domain. Just as adding to complex numbers was a vector addition. Okay, so when you said that, for example, I have two vectors p and q. Okay, I want to understand what it means. Let's say we fix one of the complex numbers, small p. Okay, so small p is some fixed number, and q is variable. Okay, so I want to interpret what it means adding p to any complex number. So when I add in this diagram, for example, q started here, and to q I added p. So when I added p, q went to this new location r. So in a way, do you see that adding p is nothing but applying this vector displacement to q of some fixed magnitude and direction. So no matter where q is located in the plane, maybe q is located over here, adding p will mean that the new location of q after adding p will go somewhere here. So the same vector of that magnitude and direction will be applied to q, no matter where it is in the whole plane. Right? Do you follow that?
Yes, sir.
And I can take this further to any set also. So let me take any object in the plane. Maybe let me take a circle. Okay. So there is a circle over here, and I can talk about adding the variable p or the complex number p to this whole circle, which means I have to add p to every element, every point one by one, and every point will be displaced in the same way. The whole circle will be translated by this vector to a new location. Okay. So this is a geometric transformation which we call translation. Okay. So the object remains congruent to itself, but its location has been changed now. So this is how we can interpret addition in the complex domain. Similarly, look at multiplication. Now multiplication is a bit more complex, but ultimately you will see that it is also quite easy to understand once you get the basics. So again, the setup is the same. Let p be a fixed number value. Okay, so let me say, so this is 1 comma 0, and let p be some number over here. So the capital P is the point, and its complex coordinate is small p. So now I want to interpret what it means to multiply any complex number in the plane. So if I have any other complex number q over here, what happens when I multiply q with p? So do you have already some idea? Okay, so how about this? So what we saw earlier, then we said that by multiplication of polar coordinates. So if the polar coordinate of P is r comma theta, and suppose Q has some polar coordinate r1 comma theta 1, then when I multiply Q by P, I'll be multiplying the modulus r1 by r. So the new modulus will be r1 times r. Okay. So wherever that new point lies, its modulus will be r1 times r, and its angle will be theta 1 plus theta. Correct?
Yes.
So if we do
Yes,
these two operations one after the other, okay, let's say we first rotate by angle theta. Okay, so this angle theta, if I rotate for point Q, so it may go somewhere here. So whether this angle is theta, right? So that same angle theta I am copying over here. Okay, so Q will go somewhere here, followed by which I have to also multiply the argument by r. So in other words, I have to translate or displace this point farther away by that ratio r. So this will be my new point r. But now I want to see what is the connection of this point OQR with the original point P. For that. So for that, this point is important, the unit point. Okay, the point which has coordinates 1, 0. Okay. Unfortunately, my diagram doesn't make it very easy to label. Let me just call it point U. Okay. So the fundamental thing I want all of us to observe is okay. The basic thing is, can you see that triangle OUP is similar to triangle OQR? I mean, it also appears in my diagram, roughly speaking. But can you see why this will be true? That triangle OUP is similar to triangle OQR.
SS.
SS, correct? I don't know why my laptop keeps switching off the other way, but anyway. Just give me a minute. Used to be some problem. Can you hear me?
Yes, sir.
yes, sir.
Okay, this is very weird. So my account is getting signed out, but apparently Zoom is still active. But I can't see on the screen what I'm sharing. So yeah, by SAS test you can see that, because basically OP upon OU is R upon 1, which is equal to OR upon OQ, and the angle in between is obviously theta. So what this means is that there is a spiral homothety that takes the point U into P around origin, important to see. Okay, so when I say a spiral homothety, it's a combination of a rotation and a dilation. So it is a rotation through angle theta and dilation through the value of r. So I mean, everything is well defined over here, the r comma theta. Okay, but the same homothety is also responsible for taking Q into r. Okay, so the important point is that these are the same homothety. So in a way, just as I was asking you to imagine that when you do the translation, when you add a complex number, you are shifting the entire plane to the right or up, what is the direction, by that fixed magnitude vector. In the same way, multiplying by complex number is nothing but applying a spiral homothety to the whole plane. So it's like you are grabbing the whole plane, rotating and dilating it. Okay. So point by point, every point in the whole plane will get offset like that. In particular, so if there is a locus on which Q belongs, okay, if suppose Q belongs on some circle, then its image R will also belong on a larger circle. Okay, and this circle is nothing but a spiral homothety of the original circle through this combination of R and theta. Okay, are you able to follow this interpretation?
Yes, sir.
So, so this property in particular is what makes complex numbers so powerful. So if we try to put all of this together and actually solve a problem to see how we can use all of this information. Uh, okay, let's start with something like consider triangle ABC, and on each side, let us draw a isosceles right angle triangle. Okay. Prove that AP these three lines are concurrent. AP, PQ, CR. Does anybody already know a way to prove this kind of property?
Yes, sir.
Okay. So I think you may be aware of the Sevas theorem kind of proof for this,
Yes, sir.
right? For those who don't know the Sevas theorem proof, so I will not disclose it, but suffice to say, you can try it. I mean, consider, for example, a trigonometric Sevas theorem and things like that. Okay? But this can be done with standard geometry also. But now I want to see if we can do this thing with complex numbers. And the point of using something like complex numbers is that we can generalize this to some different results also. Okay. So to apply complex numbers in a problem like this, the first step is to, of course, start by assigning complex coordinates to every point. Just as if we were to use traditional coordinate geometry, we will set up some like XY axis and start giving coordinates to every point. In the same way, here I want to start giving coordinates to every point. So in particular, as I said, that the convention is to use the lowercase letter for every point. Okay. So now in this, the coordinates of capital A, B, and C, those are what we can call the independent variable because we cannot choose which triangle we are talking about. Okay. So basically, like A and ABC are our basic variables. And if we can write the coordinates of PQR in terms of ABC, then we can try to solve this problem. Okay. So for example, can you find out what is the coordinate of P? So in other words, can you write P in terms of ABC? Okay. So this is how we can do it. And almost the way we express this answer, this will show why complex numbers can be so powerful because we'll almost write a recipe of reaching the point P. I mean, I did not specify where my coordinate system was, where is the origin and etc. Turns out it doesn't matter. Okay, let the origin be anywhere it wants to be. Okay, and now I want to reach the point P. So just as on a map or somewhere, you will see the directions that go here, then turn left, turn right, etc. In that way, we have a procedure to reach P from O. So from O, first, let us reach the point C. Okay, so O has coordinate 0, obviously. So I won't write 0. Plus, so to reach point C, we know that the vector which goes from 0 to C, if I just add it 0 plus C, I'll reach the point C. Okay, as I said, I don't want to write 0 plus, that is silly. But basically we reach the point C now. Now from C, I want to reach CP. Okay, so to reach CP, I could add P minus C, for example. Okay, but this doesn't seem to be very helpful. But now what I can do is look at this triangle BCP. Okay, if I take C as my center of homothety, spiral homothety, do you see how B and P are related to each other? So with C as the center of spiral homothety. So what is the spiral homothety I need to consider, which will map B into P? So what should be the angle and ratio?
Sir, 45 degree and 1 by root 2.
So I could consider angle 45 degrees and ratio 1 by root 2. Is that fine? So if I apply this spiral homothety around point C, then B will go into P. So therefore, what I can do is this P minus C. So this vector basically, this vector and this vector, they are related by the same expression. So B minus C. So B minus C is nothing but the vector CB. Okay, and P minus C is the vector CP. And as I just explained, CP is nothing but CB with this spiral homothety of ratio 1 by root 2 and 45 degree. So therefore, what it follows is that this number should be nothing but this number multiplied by the complex number whose polar coordinates are 1 by root 2 comma 45 degrees. So in other words, what is that number whose argument is 45 degrees and modulus is 1 by root 2? If this is your origin, this is 1 comma 0. Do you see where that number goes? Basically, I can draw a small isosceles triangle over here with one vertex at the origin, another vertex at the unit point, and wherever the third vertex lands, that will be that number, special number Z. Okay. So if I multiply any complex number with this Z, it is as good as performing a 45-degree rotation followed by 1 by root 2 dilation. Okay, and I mean in the complex the polar system, the Z has the coordinates 1 by root 2 comma 45, but in normal Cartesian coordinates, what is the coordinate of Z?
Sir,
It is half plus half I. Okay, so this half plus half I don't want to keep writing half plus half I every time, so I'll just call it Z. But we know that Z is equal to half plus half I. Okay, so I know this, I can plug this value into this expression, and what I get is P is equal to C plus Z times B minus C. And important note, Z is a constant here. I mean, it's just like a normal number that we have. Just for simplification, I'm writing Z. I could, every time I could write half plus half I also. Okay, but the important thing is that I would be able to express the coordinate of P completely in terms of ABC. In fact, point A is not required here also. Okay, are you able to follow this? If you want, I can repeat any part. Okay, so important thing here which you should note is how we use the multiplication interpretation and its connection with spiral homotheity. That multiplying with a complex number like Z is nothing but this performing this rotation and dilation. That is what allowed us to use this kind of expression. Okay, so if we continue this way and do the same thing for other points Q and R, in fact, I don't need to look at the diagram also. Just by pure symmetry, I know what is the expression going to be. Okay, so the coordinates of P, Q, R, all of them are now represented in the complex variables. But that doesn't help us to understand. Finally, we want to show they are concurrent, this AP, BQ, CR. So how will this help us to show the concurrency? So for that, if we think about it, right, this line AP. Okay, so every point on this line, so we all know section formula from 2D coordinate geometry,
Yes, sir.
right? So every point on this line will, we all know in standard like coordinate section formula kind of approach. If I take, suppose they are going to be concurrent at some point, okay, some point S, let's say. Okay. So then the ratio AS is to SP. In terms of that, I can find out the coordinate of this point S. Now turns out we can do the same thing in the complex domain also, because the addition is perfectly linear on both x and y axis. So if let's say the ratio AS is to SP, so let me just draw that line separately over here. So let's say this ratio AS is to SP is lambda upon 1 minus lambda. Okay, then in the normal, just the way we have written section formula, that let's say the x coordinate of S would be AX. So I'll write the x coordinate of the two endpoints, and I have to multiply them with the weights by sort of cross multiplication. So A gets the weight of 1 minus lambda and P gets the weight of lambda, and divided by lambda plus 1 minus lambda. So that's why I deliberately took in them in such a way that the sum is 1. So ultimately it's just 1 minus lambda AX plus lambda times PX. So the same thing is applicable in the complex domain also. So S can be written as, so now the advantage is I don't have to consider x and y coordinates separately. I just have to write one equation, and that captures both the x and y coordinates, which we would typically do separately in the real domain. Okay, so that point of concurrency will be something like this. So I just have to figure out some point which lies on all the three lines. So the lines which we are considering, AP, BQ, and CR, if I can figure out some value of lambda, I mean, so here the value of lambda is connected to line AP. But if I can get some S which is symmetric in both all three of ABC, then it has to lie on all the three lines. Okay, so all we now have to figure out is what is the value of this lambda. So if you look at P here, for example, and remember always Z is nothing but half plus half I. So if I substitute the value of P from here into this expression, I'll get S is equal to 1 minus lambda A plus lambda times. So now, as I said, my interest is in terms of the coefficients of A, B, and C. So let me expand it that way. So lambda Z times B plus lambda times 1 minus Z times Z is 0.5 plus 0.5i. So if I can figure out some value of lambda, which will make this whole expression symmetric, then we are done. Okay, so these values are 1 minus lambda. So now I'll actually write out everything in terms of the complex values. Okay, then this is 0.5 lambda plus 0.5 I times lambda. This. Okay, by the way, when Z is equal to this, what is the value of 1 minus Z? Okay, it is just one of the signs is flipped. Actually, I'm stuck here, but just give me a minute. I'm not able to remember what is the next step actually. Okay, maybe I need some time to revise this proof because I'm not able to figure out what is the next step here. But in general, I mean, the idea which I want to indicate here is that, so assuming that it can be done, okay. So this point of concurrency S, we get some coordinates in terms of A, B, and C. Okay. something A plus something B plus something C. Okay, so there is a special name for this kind of coordinates. In particular, when it turns out, I think it turns out in this case also, but I don't remember, these coefficients alpha, beta, gamma, right? So they are real numbers ultimately, and their sum is 1. Okay. So there is a special name for such coordinate. They are called barycentric coordinates. Okay, and what they represent is in the plane, right, in a triangle. In a way, this is connected to Seva's theorem, because I mean here we are doing a concurrency problem, so obviously we were using Seva's theorem. I mean, if the other geometric proof, we would have used Seva's theorem, for example. But in general, what happens, right? Every point in the plane, and this is applicable to the exterior of the triangle also. But to begin with, let us take a point inside the triangle. Okay, so if you consider these three triangles. Okay, so in the proof of Seva's theorem, you may recall that the areas of these three triangles are important. So turns out that the area of, for example, PPC, etc. So the ratio of the PPC to the area of the whole triangle ABC. Okay, so if I call this ratio as alpha, okay, so alpha because it is opposite to vertex A. Okay, so this area is alpha. Rather, I should say this area is alpha times delta. Okay, so if I call delta as the area of the whole triangle ABC, then this smaller triangle has area alpha times delta. Similarly, I could call this area as beta and this as gamma. Okay, so beta is the area of PCA upon delta, and gamma is the area of PAB upon delta. Okay, then as it turns out, the complex coordinate of P can be written as A alpha, or let me write alpha A plus beta B plus gamma C. And you see this alpha, beta, gamma satisfy these properties, that their sum is 1.
Yes, sir.
Right. So these alpha, beta, gamma triplet. So basically it's a 3, might be funny to see that in a plane, why do you require 3 numbers to uniquely define a point when 2 are sufficient? But there are some useful properties of having this extra degree of freedom. But then you realize that you don't really have a degree of freedom, because you cannot choose alpha, beta, gamma arbitrarily. This constraint is there. So in a way, even if you have 3 equations, the degree of freedom is only 2, because if you choose alpha and beta, then gamma has to be forced to be 1 minus alpha minus beta. So the degree of freedom is still 2, but the symmetry in terms of ABC is what makes this powerful. And you can start to see examples of like where I take this point P in various locations around the triangle, and how these values of alpha, beta, gamma change. For example, if I take the value of alpha, beta, gamma as 1, 0, 0, it means that basically the point P is at the vertex A. Okay, so basically the vertex A has the coordinates 1, 0, 0. B has the vertex coordinate 0, 1, 0. C has the vertex coordinate 0, 0, 1. Like that. So for example, what would be the coordinates of the centroid? The centroid of the triangle. See, each of these triangles is 1/3 of the whole, right?
Yes, sir.
Okay. So the centroid has barycentric coordinates 1/3, 1/3, 1/3. So in a way, I mean, this problem which we are doing here, I'll figure out how to finish this proof. But this point of concurrency we are trying to figure out, that will also have some barycentric coordinates which are symmetric in terms of ABC. Okay, so all the standard good points that we have, like orthocenter, circumcenter, incenter, all of them have very nice barycentric coordinates. And this will be also important tool in the way when we try to use complex numbers for more advanced proofs. Okay, and turns out there is a nice interpretation of these barycentric coordinates in a completely different domain. So by the way, I'll have to finish our lecture early today in the next 5 minutes. But just to finish up on this point, like in lieu of a puzzle, just want to explain how these barycentric coordinates turn out to be important in a field called 3D graphics. So, I mean, you may know that I work at NVIDIA, which deals with things like computer graphics, animation, games, things like that. So, in that field, these barycentric coordinates have a special importance because, as it turns out, like any graphics that you see, maybe it's some computer animation or some movie, uh, the characters that you see on the screen, right? I mean, you may, for example, look at a sphere and it may look like a sphere, but in reality, in the sort of computer model, it is just composed of many small triangles. So it's like millions of small triangles are there on the screen. Okay. And just because they are so tiny, just like pixels, so we think that it's a smooth surface, but at the core, it's just a number of triangles. Okay. So every triangle that is drawn on the screen, so the artist, the digital artist, the cartoonist, or whoever who created that animation, let's say, they don't have the time or it's not possible to go and paint every pixel of the screen one by hand. Okay, so it's not possible to color every individual pixel. But what the artist can do is color the three corners of that pixel. Okay, so let's say they give the corners some three colors: red, green, and blue. Okay, now it's the job of the computer software to figure out what is the color of every individual pixel in between. So that is where they use barycentric coordinates, because basically every point in between, whatever is the alpha, beta, gamma coordinate of this point, that is the amount by which the three colors have to be blended. So if the point is closer to this first vertex, then it has to be mostly red and less blue, green, etc. So basically the transition of the colors has to be smooth from one vertex to the other. Not only that, the transition between adjacent edges also has to be smooth. So if there is a triangle here and another triangle here, okay, so then at the boundary, basically the color should not appear as suddenly changed. Okay, so all of those things get taken care of very nicely if you use the barycentric coordinate to figure out how to mix the three colors. Okay, so that's like one very cool interpretation of barycentric coordinates. In these are what are called pixel shaders actually. Okay, so yeah, I mean this geometry that we are doing also has a lot of other application. Like I don't know if you had expected that Sevas theorem is important to play computer games, for example, something like that. Okay, but anyway, I think we are going to stop for today. I'll suggest you to also try and think about this proof. I don't know if I made some mistake in the calculation, but we can figure out how to finish this idea. But as I said, the key point is, can you figure out a value of lambda such that this S has symmetric coordinates in terms of A, B, and C? Okay, then it should be doable. Okay,
Sir,
that's all from me. You want to ask anything?
sir, in that proof, we can prove that triangle PQR centroid and triangle ABC centroid is same. So there exists transformation. Can we do by that?
Okay, even if the centroid is the same, if the triangles are similar, then the transformation would make sense. But if the triangles are not similar, then what transformation are we talking about? I think your point is valid. The centroids may turn out to be coincident, but that doesn't mean anything on its own, right? And when you have many triangles in the plane might have the same centroid, but that doesn't mean their corresponding vertices will be concurrent. Okay, does that make sense?
Yes, sir.
Yeah. Is it, as it turns out, for some reason that PQR and ABC are similar triangles also, then I think what you're saying, there could be some ideas around that. But I mean, at least from my memory, I don't think that is the proof. Let me see offline if I can figure it out. We'll continue next time. Okay, I think that's all from me. Thank you. Bye.
Thank you so much, sir.
Sir, bye, sir.
Thank you so much, sir.